Hello, this is the fourth video in the CPA series for OCR Discrete Further Maths, and it considers the finding of critical activities and critical paths. In session 1.3, we found that the minimum project completion time is the duration of the longest path through the network. We also found latest event times and earliest event times via forward and backward passes. We saw that for some activities there was some flexibility as to when they started or finished, whilst any delay on other activities would have impacted on the overall project time. So, the delay on the longest path will lengthen the whole project completion time, and this is then the critical path. And the activities on the path are called the critical activities. We defined float as the flexibility or spare time associated with an activity. It is important as it gives us information about the impact that a delay on one activity will have on the whole project. Activities with zero float, in other words no flexibility, are the critical activities, and these will lie on a critical path. Float becomes very important when scheduling activities, as the spare time on non-critical activities can be used to delay the start of some activities. If you go on to A level, you will cover this then. Scheduling may enable a resource, such as a person or a machine, to carry out more than one activity without affecting the project completion time. Again, this is covered at the next level. We can find the total float for an activity F, denoted by the start and finish nodes I, J, by finding the latest event time for J, the earliest event time for I, and then also subtracting the duration of the activity at nodes I and J. An example that we looked at in the previous video showed activity E, which at node 2 had an early event time of 4, a late event time of 5, and at node 5, early event time 17, late event time 18, and duration 13 time units. So the total float for activity E, where we have the outside boxes, the latest event time would be 18, minus the other outside box, the 4, the earliest event time for it starting, minus the duration of activity E, which would give us 1. For a network then, where we have already completed the forward and backward passes and found those timings of early events and the latest event times, we are looking for a zero float on the activities, as this would indicate that they are critical activities, i.e. there is no flexibility. For activity A, we would have the outside box, take away the other outside box, take away the duration. So in other words, 6 minus 0 minus 6, which gives us 0. So A is a critical activity. For B, we would have the outside box 5 minus the outside box 0 minus duration of 4 equals 1. Therefore, we have a float of 1 for B, and it is not critical. For C, we would have the outside box of 20 minus the outside box of 0 minus 15, giving a float of 5. What this means in effect is that C could start as late as time 5 and still be, of course, completed in time for 20. C is not critical. For D, we have the 16 outside box minus the 6 outside box minus 10, which would give us 0, so D is critical. E, we already know, has a float of 1, so is not critical. F, the outside box of 20, minus the early event time 16 minus 4, 0, so F is critical. And for G, we have outside box of 20 minus the outside box of 17 minus 2 equals 1. So G has a float of 1 and therefore it is not critical. So we can see that the critical activities are A, D and F, and these will all lie on the critical path. So the critical path is shown in red on the slide. So A, D and F as the critical activities must be completed in that exact time window, or the whole project is delayed. You will notice that along the critical path, the boxes show left hand and right hand of the same number. In other words, the early event time and the latest event time are the same. Do be careful though, because in some circumstances, having the same number in both boxes does not always mean the activity is critical. You do need to work out the floats. You may wish to pause the video here and try forward and backward passes in this example for yourselves. So I would start with a 0, that would then be a 4. This would be a 6, you'd think, because of the time taken for B, but actually I also need to complete C, which will be 3 plus 4, so that will therefore be a 7, choosing of course the largest numbers on the forward pass. Here 7 plus 3 is greater than 4 plus 4, so I will put a 10 in this box. Thinking about that, then I have a 4 plus a 7, which would be a 11 in this box here, which is greater than 10. And then considering node 6, that will be a 10 plus a 2, which is the same value actually as the 5 plus 7, so a 12. Node 7 will be either 11 plus 3, 14, or 12, or 14 is the larger, so that becomes a 14. Node 8 will become 19, and then 14 plus 3 would be 17, but I have a larger 19, and a 12 plus 9 is the largest, which is 21. Moving backwards now, I start with 21, sorry the box is a little small, and find then that then has to be finished by 21. That 21 take 5 will mean a 16 rather than 18 in that box. The 18 you might have thought from the 21 minus 3 when we're taking the smallest numbers on the way back. 21 take 9 will give a 12 in that box, leading to a 7 there. We have 12 take 2 is another 10 in that box. We have down to 16 take 3 is a 13 there. We have a 4 in that, because we have gone from a 13 take away 7 would give us a 6, but we have had a 7 take away 3 to get back, so that's the smallest number, so that's a 4, and then as expected a 0, 0 there. Whilst we've got this example, it's also worth noting that in some cases you may be presented with a network and asked to work backwards to a precedence table. example here, A and B would have no preceding activities, whereas C, D and E all rely on A, F relies on B, C, as does G, H relies on E, F, and I relies on D, E and F, J on G, H, K on G, H and I, as does L. You may also be asked why the dummies are required. So make sure that you can tell the difference between dummies required for precedence and dummies required to preserve unique identity. That said, we are actually asked to identify the critical activities and paths for this network. So having established the early event times and the late event times via our forward and backward passes, we are now in position to check the floats. The float for A will be 4 minus 0 minus 4 being 0, so A is critical. For B, 7 minus 6 minus 0 is 1, so not critical. C, 7 minus 3 minus 4 is 0, so yeah, C is critical. D, 13 minus 7 minus 4 is 2, and E, 10 minus 4 minus 4 is 2, so neither D or E are critical. F, 10 minus 3 minus 7 is 0, so F is critical. G, 12 minus 5 minus 7 is 0, and H, 12 minus 2 minus 10 is 0, so both G and H are critical. I, 16 minus 3 minus 11 is 2, so not critical. J, 21 minus 9 minus 12 is 0, so J is critical. K, 21 minus 5 minus 14 is 2, and L, 21 minus 3 minus 14 is 4, neither of which are therefore critical. Thus we have a number of critical activities, and then also we have more than one critical path, as marked on the diagram. So the option you can see is rather that A, C, F, H, J are critical, you could also have a path A, C, G, J as well, as shown by the dotted line. So to summarise CPA, the steps are to prepare the network by listing activities and creating a precedence table, to draw the network with activities on arcs and events, so start and completion of activities, as nodes, and to use dummies as necessary. To analyse the network by calculating the early event times, the forward pass, choosing the largest numbers, and the latest event times, the backward pass, choosing the smallest numbers. Then identify the critical activities via the float calculation, with critical activities having 0 float, and the critical path that they lie on. You may also be asked to calculate total floats on non-critical activities, or even to develop a precedence table based on a network given to you. Once you've done all this analysis, you may then be able to assess the impact of any delays or changes to activity duration on the overall project and advise accordingly. This is the last video in the CPA series.